Okay, so stiffness and strength are not the same thing. Okay, you can make something both flexible and strong. Okay, and you have 3 tools in your compliant mechanism handbook to make, or compliant mechanism toolbox to make things more flexible. They are material properties, geometry, and boundary conditions. And you saw that in his presentation, right? You saw things where boundary conditions, for instance, of fixing both ends, it changed everything. Changed how stiff it was or flexible, and obviously changed the material properties. Okay, sorry, we got wrong stuff up here. I can read all my email. That could be bad. Okay. Oops. Okay, maybe a little story here too. So to start out, so going back, the idea is you can flexibility and strength are not the same thing, or stiffness and strength are not the same thing, and also that you can make something both flexible and strong. And it's not intuitive. So once I had some people come in for some consulting, and they had a metal band that they wanted to go through, and it was going to go around a pulley. Okay, oops, I was hoping I made it too stiff. And it's going to go around a pulley, and then and then they had to connect. It was going to go around the pulley and come around, and it was connected to itself, right, where it would be welded. Okay, so but the difference now is instead of taking the idea on that is it wasn't to take a force like we're often doing if, say, you're designing a connecting rod or something, right? It had to undergo a displacement that's different. It needed to be flexible, okay, in order to go through that motion. And they came to me and they said, "Oh, Dr. Howell, this here where we weld it keeps breaking, and so we're coming to you, ask you to tell us how thick we need to make it so it doesn't break." And they said, when we first did it the first time, and it was going, around, and it broke. So what we did was we beefed it up. We made it thicker. Okay, which in most things, that's what you would do, right? But what did making it thicker do? Increased its stiffness. But now, I'm not trying to take, in this case, I wasn't trying to take a load like this on a beam. I was trying to undergo a displacement around the pulley. So they said when we thickened it up, it broke even sooner. And I'm nodding my head. I say, yeah. And it says, so what we did was we beefed it up some more. Right? We made it even thicker. And it broke even sooner. Okay, so they're doing exactly what works on every other engineering project that they had done, but when they started designing a compliant mechanism, okay, it was behaving differently. And I, nodded and says, yeah. So now what we're doing is we're coming to you. We can't just keep doing this because this is expensive. So we've come to you to have you tell us how much do we need to, how thick do we need to make it? How much should we beef this up so it doesn't fail? And I explained to them, well, what you're doing, you're going through displacement loads. You actually need it to be flexible, not stiff. It will actually be strong. It will not fail if you make it more flexible. Okay? But now, if you think stiffness and strength are the same thing, you can't get that into your mind. That doesn't make sense, right? And so I explained to them, no, what you need to do is you need to make this more flexible. It'll actually decrease the stresses by making it thinner. And they look at me and I'm like, no, 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 you don't understand. Okay? It's failing. It's breaks. We need to know how much thicker do we need to make it so it doesn't break. So I explain, okay, this is, you want it to be more flexible because it needs to go through this displacement load, and you need to make it thinner. And they're like, no, 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 no. You don't understand, okay? We're trying to make it so it doesn't fail. And I'm like, yes, I know. And then eventually they're like, these professors in their ivory towers, they don't know anything about the real world. And they stomped out and refused to pay the consulting fee. So anyway, okay, so there are times where it's that simple concept is really, really important. Okay, one other story is, I mentioned I teach a class on compliant mechanisms. I had a student graduate, and he was working at a large company that makes computer products, and likely sometime in your life you've owned a product from this company. And he was working on basically snap fasteners, which was really early on in the industry where they were doing this. This was before the book had come out or anything, and so this was a while ago. And they were, and they wanted to take these computer components and snap them in without needing fasteners and everything. So you've seen it. It's kind of like the back pouch latch. And this student got there, this graduate got there, and he saw their components kept failing because it needed to go through a displacement load. Okay, kind of like this backpack latch. But now it's a snap fastener on computer electronics. And they were doing the same thing. It would fail, so what did they do? They made it thicker. And this guy got there and he said, oh, I see your problem. It's too thick. Or actually, the first job they gave him, the same kind of job as what I described, is he got there and he says, oh, you're new. We want you to learn. We're going to give this. These keep breaking. Okay, we want you to fix this. Decide what the geometry should be and everything so that these don't break. How thick does this need to be? And he looks at it and he tells his boss, says, oh, no, you need to make it thinner. And of course that freaks him out. And he says, no, you need to go calculate how thick this needs to be so it doesn't break. It's like, no, you need to make it thinner because it's going through a displacement load, and it needs to go through that displacement, not carry that load. And it's like, what are they teaching these kids at the university these days? They can't even beef something up so it doesn't fail. Okay, and so this guy calls me and says, what do I do? This is my boss, and I'm telling him, I know what has to happen. I know the physics here, but he won't listen to me. And he doesn't believe it. Can you send me some stuff? So eventually he did get him convinced. And how did he convince him? Built prototypes, okay, for one thing. Okay, you show them. And then that works. And, of course, you see those everywhere now in the industry. So it's so some of these simple concepts are not intuitive. And even to very experienced engineers who are used to designing for taking force loads instead of displacement loads. Okay, and so here, you have some opportunities to kind of challenge that intuition. All right, so we're going to talk about pseudo-rigid body model. And this is an opportunity for us to try to simplify and visualize large deflection motions. And so the philosophy in design is often to start with the very simplest model possible and then design with those simple needs, with those simple models, and then refine and validate the design with more complex models or testing. So I used to do a lot of consulting on ANSYS with finite element analysis. And I worked for a consulting firm where we made all of our money doing this because people would start out with really complex models. They couldn't get it to work, and they would come to us to get their models to work. And all we would do is we'd go back and start with very simple models and make it more, and then gradually make them more complex until it would solve it. And it's a really powerful way of doing, especially if you're going to do design, because you can iterate a lot with simple models. And similar to what we were talking about in the previous presentation of having those analytical models and things can be really powerful. So we'll often, you can start with small deflection equations, and then, we'll show you the pseudo-rigid body model. And there are other, we've seen these other approaches and stuff too, and you can also take the pseudo-rigid body model and, use computer simulation, and then nonlinear finite element analysis. So we'll often go through this series of things and then refine the model or refine the, Okay, so pseudo-rigid body model in particular here. So what we're going to do is we're going to model compliant mechanisms as rigid body mechanisms. And so that allows us to use all these decades of research that's been done in rigid body mechanism analysis. And we're going to be able to use that. Everything, all this stuff you see at the DETC and the Mechanisms of Robotics conference, now we can use to help us also design compliant mechanisms. So we'll say often that this unifies compliant mechanisms and rigid body mechanism theory, so we can use those both together. So, all right, some of you have seen this before, so you can't answer the question, okay? So this is a little quiz here, just to test your intuition. I'm going to come in on this flexible blob. So this here represents where it's fixed to ground. So these are fixed points, okay, where those are rigid fixed points to ground. These thin parts are flexible, okay, and these thick gray parts are rigid, okay? So can you see what's going on here? So this flexible blob here with some parts that are flexible, some that are compliant. So the question is, what if I come in and I push on this part right here with those fixed to ground? I'm going to push on this. What direction will that point right there go? Okay, so look at that. So if you've seen it before, because I've used this in other examples. So, all right. So we're going to vote, and there's, everybody, you need to vote if you haven't seen it before, and we'll just see where we're at. So I'm going to say move to the right, that this will move to the right. Okay, I've got 1, 2, 3, okay. Okay, 4, 5, okay. How many to the left? Okay, a couple about the same. Okay, up. Okay, 1. Okay, down. Okay, a few more. Okay, all right. So looks like the right, going to the right, the vote won. So it moves to the right. It's a democratic process. Okay. Now we'll come back and we'll see here in a minute what it does. We're going to have the pseudo-rigid body model help us. So this crazy-looking blob, right, is, who knows, right? I could put this in finite element analysis and figure this out, or we're going to look at the pseudo-rigid body model. Okay, but first we're going to take a few steps on this first. So if I have this flexible, this part here where I have some flexible part that's really short in length compared to this rigid part, and we say that the flexible part is much smaller than the rigid part. Then when we do that, there's an easy way to model that. Let's look at an example here. So here's where we're actually using 4 of these, okay, in that. What would be one way to model that motion? Yeah, pin joints with torsional springs right there, right? Say, hey, that most of that motion is happening right there at those points. Okay? And so, know, we can have a very simple model, okay, very rough, very simple, that says, oh, I can put a pin joint right there with a torsional spring that represents the resistance to motion. Okay, and now I have a very simple model of that. And if I do that, then this doesn't have the torsional springs, but it does have the, the pin joints there. And it's just right in the middle of that flexible segment. And I see, by golly, that's pretty large deflections, and that's pretty close motion, right? And so that seems like a reasonable model then for this simple case. And let's what we're going to do is we're going to kind of create a library of these pseudo-rigid body models, and this is the first one. Oh. Let's see. So we have a small length flexural pivot. And we're going to say it's pseudo-rigid body model. Just has a pin joint here at the middle. And if this is L, and this is capital L, lowercase and uppercase L's, if that pin joint's at the middle, what's that distance there? What's half of lowercase L? Okay, L over 2. Okay, so that's L over little L over 2. So what's this distance? Okay, yep, capital L plus little L over 2. Okay, so that's a pretty simple model now where my rigid segment, okay, is defined there, and then I'm going to put in a torsional spring here to represent the resistance to motion. And I'm going to give that a spring constant K. And it turns out, we're not going to go through and derive all this, but that is the Young's modulus times the moment of inertia over lowercase l. And that turns out to be a really good approximation, surprisingly, for reasonably large deflections, even if, well, especially if little l is small. Okay, I don't know, can you guys see those? I might need to move this up closer. We'll see. That's all right. Okay, so let's look at the next thing here. And also related to this are what we call living hinges, which are just really extremely short and thin small length flexural pivots. And in this case, the pseudo-rigid body model is a pin joint at the center of the flexible segment. And if there are any other compliant elements present, then you can usually, just ignore the living hinge. So here's an example of just a consumer product, right, with the living hinge. So you've seen stuff like this, right? Just one piece of molded polypropylene, and that you can see we can model that really closely as if that were just a pin joint there, right? And that would be a very accurate model, especially for something as simple as this. If I were just designing a soap container, right, I don't need super high precision in doing that. And then I also have, notice this guy here is just a beam, okay, that's coming up over there, and I get deflection of both that part and that part. But that beam right there, actually, I could also model as a small length flexural pivot. Okay, so that's a small length flexural pivot and a living hinge. Those there are also living hinges in those forceps we showed before. Okay, so I have 4 living hinges there. And by golly, I can model that as just pin joints at each one of those positions. And if I do that, then this guy here becomes really easy to model. Oh, okay. Wrapper's still on there. So. Yeah, no, we're good. I just was being dense. So now we say, hey, you know what? I'm going to put a pin joint here, pin joint here, pin joint here, pin joint here, and I have a model that looks like this. And now, sorry, that's not a very, but you've got the ideas. Turns out that's just a 4-bar mechanism. I can use my undergraduate kinematics to analyze this device. Okay, and so that makes this a very simple device to design. Okay, so there's the simplest example there. Now let's move on to some others. Okay, so the next one is what we call fixed pinned, meaning it's fixed on one end and it has a free end here, which means it only has a force. There's no moment at the end, only the force. And if we do this and look at this deflection, that can go into very large nonlinear deflections. And we saw equations that can work on those. And if you get even larger deflections, really large deflections, to do analytical solutions, you end up using elliptic integrals, which you can do, but they're a real pain in the neck to work with. And so, but now what if we want to go through this large motion? It turns out that there is a model for this that is still really accurate. Let's see, I think I was trying to help with this, so now I'm blocking the screen. Sorry. Trying to fix one problem. That's what engineers do, right? You fix one problem, and so you fix the need for transportation, and you create internal combustion engines, and then you cause global warming, and then you go fix global warming, and then who knows what you'll cause doing that, and then it's just great job security, right? So, okay. Let's see. So here we found, and this was actually one of the coolest things in my career as a young engineer was discovering this concept that you could take this large, we're doing analysis in elliptic integrals and everything, and then some pretty complex nonlinear numerical methods, and then when we discovered that we could model this with a pseudo-rigid body model with a pin joint, now not in the middle, but at another location here, specific location. And how this happened was, as I was looking at this with elliptic integral solutions, and started to notice that this path that it was going through looked an awful lot like a circular curve. And it wasn't exactly like a circular curve, but it sure looked like one. And so And all the other people that had been doing this in the past had always plotted, the vertical deflection versus the force, and the horizontal deflection versus the force. But I didn't care about that. What I cared about was the motion in space. And so I started doing that, and people had just not looked at it that way. And I started to plot the motion in space. It's like, wait a minute, that looks kind of like a curve. So I literally took a compass. You guys ever seen a compass? Okay. But it's mechanical, so you take a compass and started to swing arcs and started to look and find, it's like, holy cow, that was going through a path that was nearly circular. And so then once I discovered it was nearly circular, ran an optimization routine to find the very best position that would best find or best follow the path. So it's not exact, but it's still pretty accurate. And so what we determined, we called this the characteristic radius factor. And Ashok Mehta was my PhD advisor. And we did this sometimes. He's referred to as the father of modern compliant mechanisms. And this pseudo-rigid body model was was created. So here we have a couple of things we have to worry about. We have to worry about the spring constant here. We have to worry about this gamma, which tells us where this is. We call it the characteristic radius factor. And then there's this angle here, what we call pseudo-rigid body model angle. That does not match what's happening with the beam here, right? So this capital theta is just in our model. So if we look at this, so this is the horizontal position and the vertical position, non-dimensionalized with the force. So here's the elliptic integral solution, closed form solution showing its motion, and then also where the pseudo-rigid body model approximation falls. So really pretty close. So even think of a beam, okay, that's however long, and let's say it has a length of L. And then I take it to a vertical deflection. It's 80% of L, okay, 0.8 L. Okay, so that's a huge deflection, right? Very far into the nonlinear range. And it turns out that even with the vertical deflection, nearly 80% of the beam length, the pseudo-rigid body model will predict that still within 0.5%. Okay, so it's still a really accurate model on the path. So you're within 0.5% of the closed form solution, even up to that large of a deflection. But now it's super simple. So when I'd started as a grad student ages ago, people told me that compliant mechanisms were so complex, there would never be a day you could do something as simple as 3 precision point synthesis, which, if you've taken undergraduate kinematics, is like, what you do as an undergraduate. And from how complex it was at the time, that was probably true. But now, if I can do a model like this, suddenly it simplifies compliant mechanisms, and you can unify, right? You can bring together kinematics equations and this, and you can do it. So anyway, so here's the model. And let's come back and add to our library here. Okay, so we have a long flexible segment with a force on the end, not a moment on the end. Okay, force, and then we have the model looks something like this: a pin joint right there and a torsional spring. Oops, I wanted to do a torsional spring in red. Okay, torsional spring to represent the resistance to motion. And now this distance here is gamma times L. And here's a little secret. Or gamma can change depending on what angle your force is at. But if you use a gamma that's about equal to 0.85, that turns out to be very accurate. Okay, so it turns out that gamma equal to 0.85 is a really good approximation. And for a vertical load, it's really, really accurate. And then this torsional spring is K is equal to, gamma. Sorry, start over here. Gamma times K theta EI over L, where gamma is like this 0.85, and we can approximate K theta, which is another non-dimensionalized factor, is 2.65. So now we have both the torsional spring and the gamma, and we can model anything with that kind of a component in it. Okay? Any questions on that? Okay, we'll see some more examples. We'll have you do a couple exercises here. We'll do one exercise together, and then we'll have you do a couple more. Okay, so the practical implementation of this particular type of thing where you just have a force on the end, so it's fixed on one end, force on the other. Well, how can you really do that? And you have, things that might just be hinges there, or what we call a passive joint, what we saw on the overrunning clutch where we're moving there, or even a living hinge. And we actually see this in a lot of consumer products, where there'll be a flexible segment coming in, and then it'll get super flexible at a living hinge, and then go to a rigid segment. So if you look at your ketchup bottle, for instance, on the lid, that if it's one that's bistable and snaps back and forth, it may very well use this approach. Okay, so we'll just do one or two more here, and then we'll do some examples. So the next one is a fixed guided segment. So fixed guided is, okay, similar, we were talking about these in the previous presentation. It goes through this S shape, and now there is a moment on the end, but we force this end to remain with theta equals 0. But we are allowing it to move this way if it needs to. So it's not fixed to a wall or anything there. It's allowed to move as needed. And what the model is here, if we look at this, and you see that there's an inflection point right in the middle. Inflection point doesn't have curvature, which also means that it doesn't have the moment, because the moment is proportional to the curvature. And if there's no moment there, then that means if I break this thing, I could break this thing up as if it were two beams with just a force on the end, because internally there's no moment there. So this turns out to just be two of the previous ones combined. And so we end up with two torsional springs and a long segment there. And let's look at an example of that. Is here. So we have this this guy right here, right? And I'm going to push that and deflect that, and we get that kind of motion, okay? But what this tells me is I should be able to do a pseudo-rigid body model with these pin joints at certain locations and torsional springs to represent the resistance, and that's this guy, okay, that has those pin joints at the right locations to do that. And if you watch those holes aligned right there, then you see that motion, okay, is really close. And so it's a very accurate model. Even up to, those are pretty large deflections. Okay, so now let's, so what the pseudo-rigid body model is good for then is when you do want to go into large deflections and do these things, it's really powerful in visualizing the motion and getting the early design. If instead, if I were working on some optics, like what the Dutch are really good at, like I said, they dominate, if you don't know, they dominate the world market in these, in like photolithography machines and stuff that are used in silicon manufacturing and stuff. But now I need really high precisions at smaller deflections. That's not that great of a model because, you know, I might have a lot more air at that smaller range. Okay, but now let's say I'm doing something where I do want these large deflections, and then that can be really good for the design phase on the pseudo-rigid body model, and then you can refine it more with FEA and everything. Okay, but that should show you kind of the power of the pseudo-rigid body model there. Okay. Now, where did I put my marker? So let's add to our library here. So now we have this, but I'm going to show it in its deflected position so that we can see what's going on here. And there we have two pin joints with torsion springs. And this is, again, is gamma times L. And, oops. Yeah, there's torsion springs. And then we have here now that the K is equal to 2 times gamma K theta EI over L. Each of those. So how much? So this turns out to be 4 times stiffer than this. For the exact same beam, it's 4 times stiffer because here I have one torsional spring with just the one in front, and here I have 2 of them with 2. So remember, what was our third tool in our compliant mechanism toolbox? Boundary conditions. The exact same beam, all I did was change the boundary conditions from this to this, but I made it 4 times stiffer just by changing the boundary conditions, right? Okay, so I could also, well, yeah, all right. So while we're on that, let me just show you, here's another couple more examples of devices that use that sort of flexure. So this is something we were designing for handling silicon wafers in a clean room just to get rid of friction and particles and stuff in a clean room environment. But so now you see 1, 2, 3, 4, see 8 of those beams together. And you saw these guys, I think you showed an example of something like this in presentation too. So, and here's what we call an orthoplanar spring, which has motion that comes, it's just very flat, but then it has motion that comes up out of the plane. But then this center part doesn't rotate, it just translates out. But now each one of these individual beams is actually a one of these, okay? Okay, and during the lunch break and stuff, you'll be able to come up and look at any of the stuff I have here. Which, by the way, they told me lunch isn't till later, so don't, you know. What time's lunch? I don't want them mad at me when I'm just doing what he told me. It's not me that's holding up lunch. No. Okay, so yeah, so I think we're probably going to be closer to 1, right? 12:45. Okay, we'll say 12:45. Okay. Actually, no, we'll say 1, and it will be 12:45, and then I'll be the hero instead of the goat. Okay. All right. Okay, so now we can come back and we can look at the model of this. This crazy blob. Okay? Let's see what we can do here. What's these short things right here? How can we model those? Yeah, just with the hinge. Where? Yeah, right at the center. Okay? So I'm going to put a hinge right there at the center at each one of those. Okay? And I get, and their spring constant is just going to be, for each one, EI over L. And then these guys are fixed on both ends. We haven't talked, we'll talk a little bit more about dealing with that, but you remember the fixed guided. It looks like it's similar to that, so maybe we could model that with 2 torsional springs. And where the rigid length is centered in the middle, I didn't mention this, let's come mention this, is this is centered in the middle, and this gamma turns out is the same gamma as this, 0.85. And the same thing, that k theta is the same as that k theta because they're so closely related. And so I put a pin joint there, pin joint there, pin joint there, and a pin joint there. And we do that, and we get our pseudo-rigid body model of this mechanism. And it turns out this is a freaky mechanism. In that this is what you use in wind tunnels and stuff, that you put a model here when all you want to do is rotate it. If you look at the special geometry, that point rotates but does not translate. So it's a trick question. I gave you the choices of A, B, C, or D, of left, right, up, or down, but the answer is none of the above because it doesn't move at all. Or you could say you are all right because it moved the direction you predicted just an infinitesimal amount, right? So at this point, everything translates about that instead of, so here's some animations that show that. So look at that point right there, just kind of moving in space, and everything rotating around it. Okay, and you don't believe it, but that's okay because, believe it or not, I have some right here. Okay, so this, first we disguised that instead of a weird blob, it's an elephant. Okay, so I push on the rump of the elephant, and the question is what direction will that point right there go? And what it does is everything just rotates about that point. It just floats in space right there. Okay, and it's because what we did is we actually went backwards. We took the mechanism that was designed for wind tunnels, where we knew it had that property, but now we can use the kinematics, right? We've unified compliant mechanism and kinematic theory, right? We could take that mechanism, translate it back into a compliant mechanism, and put on some weird features here to disguise what it's going to do. And then this has all living hinges, right, instead of having other elements there. And here's one more. So the mascot of BYU are the Cougars, okay? So there's Cougar, BYU Cougar. So, and right there where his tail kind of, anyway, that's a really long tail for a cougar. He's going to get tangled up in the bush, but that's okay. And here you notice the same thing. That point right there will just float in space. And everything just rotates around that center point there. And this does use a combination of living hinges and a fixed guided segment. So sometimes people still don't believe me, and then what we'll do is we'll put this, put a pen through that hole, and then move it and watch where the point goes. So actually, maybe we need to do that right now for the non-believers among you. So we'll just put a point right there. And it might be too far away. I don't know if you can see through the hole, but you have to trust these guys up front. And it stays red in there the whole time. Anyway. All right, so there are a couple points that we can make here. One is we can use this to design, to analyze. We took these and we can analyze now, predict the motion. Plus, we can visualize what the motion is going to be. That flexible blob now suddenly becomes something that's more intuitive on its motion. And the other point that we can make is now instead of just starting with a compliant mechanism, we can actually start with a rigid body mechanism that we already know exists and work backwards. So here's an example. Oh, I hope I brought it. I meant to bring it. Here it is. So I was in China, in Xi'an, and where there's by the terracotta warriors, and my host took me to Chinese opera there that was outside, and a really impressive thing. And they bought me these opera glasses. That's little binoculars, okay, very compact, very flat, but then pop out into these little, it's about a 1.5x maybe. But anyway, but pretty cool, okay, but a compliant mechanism and living hinges, but now those living hinges are happening at these creases. But what they've done is they've taken a Saurus mechanism. If you're familiar with the Saurus mechanism, as a 3D rigid body mechanism, and they've converted the Saurus mechanism into a compliant mechanism. And so, because with the pseudo-rigid body model, you can imagine how that works, and now you can go and get the Saurus type motion in a simple compliant mechanism. Let's see. So remote. Any questions? Okay. All right, so let's do a little exercise. Maybe we'll do this one together, and the next one we'll do. Actually, you guys, you can. Well, no, we'll do this one together. We've got other examples. So, okay, so let's do this one up on the board. This is going to use all three of the tools, all the things in our library of pseudo-rigid body models. Okay. So, how would we model these flexible segments right there? How are we going to model those short ones? Which model? A, B, or C? A. Okay, because it's the flexible segments, short, compared to the long segments, or by definition, short segments are shorter than longer segments, right? Okay, the flexible segments are shorter than the rigid segments. What I meant to say. All right, so let's look at that. And we say, here we have pin joint, And we know that this, so here this is 10, looks like it's 10 units, you know, say 10 millimeters here, 10 millimeters here, 75 millimeters here. So how long is this rigid segment going to be? On my pseudo-rigid body model. Right now it is 75 is from there to there. But after I do the pseudo-rigid body model, it's longer. How long is it now? 75 plus how much here? 5 plus 5. So it's going to be 75 plus 5 plus 5 is 85, right? Okay, so we have a length of 85. Whoops, backwards. Okay. Now let's look at, let's go over here and look at this one. Okay. If this looks like it could be fixed guided. Okay, so if I take a fixed guided element there, how do I model that? Which one is that? Fixed guided, A, B, or C? Okay, okay, C. Okay, so we can, oh, and on here, we forgot our torsion springs, so we'll do that. Okay, so how long is this going to be? So this is 100. And we said there was a simple approximation for gamma, right? We said it was gamma times L, so L is 100. Anyone remember what gamma was? Okay, 0.85. So how long is this? Yeah, that's 85 also. So this gives us a nice parallel guiding mechanism again, which is nice. But we'll see what the difference is, and the spring constants won't be the same. But okay, so but we're not done yet. So this one here is a little bit trickier. It's fixed here, and it's pinned here, and this is a slider that's going up and down, okay? So this is a slider that's able to move up and down. And how do we model this one? That A is a small inflexible pivot, B, which only has a force at one end and is fixed at the other, and the other one is fixed and guided. Yeah, it turns out, this is a little bit tricky to look at it, but it is B. And the reason is because it's fixed at one place, which is here, and only has a force, which is there. Why would I say that only has a force? Yeah, because it's pinned. Okay, the pin won't take if you put a moment there, it just rotates, right? And so it's pinned. So that means it is a fixed pinned segment because only a force can happen there. Okay, so it's harder to see in that, but that's kind of why I wanted to show that as an example. So we come back here and we extend this thing out here a little ways, and then here's our pin joint, and here's the slider sliding on the wall, and this also has, well, how long is this pseudo-rigid link? So we have 100, it's the length, L is 100, so gamma is, okay, 0.85, so this is 85, okay? All right. And then we also have a torsional spring. Where's the torsion spring? At A or B? B. Why B? Yeah, because it's closer to the fixed end here. Okay, so now we just have, it's really a 6-bar with a slider here, where you can look at it as a parallel guiding mechanism with a dyad on it, with, where you have a slider. Okay, so there's the mechanism. I could put that in any kind of kinematic software or anything else that will analyze mechanisms, or I could just write the equations for that analytically, because it's not that hard, and now I can analyze that. So it looks like, or would be, a very difficult problem. And if I have this go through large deflections, right, and find an element analysis like ANSYS, I've got to have the nonlinear solvers on. There's all kinds of ways this could crash. But now if I'm designing this, I can go into, I can use this model here, do all the design, and in the end I might still take it into finite element analysis to refine the design and get all, be comfortable with all the stresses and everything. But okay, so what's the torsional spring constant for this guy here? This is a small length flexural pivot. So we have K is equal to, for a small length flexural pivot, EI over L. And so there's our E, which is 72, right? And we have out of plane thickness this way is 2, it says. 2. Wow, so it's a square cross section. That's not a good flexure, by the way. So I just recognize that it's, but anyway, that's another story. But okay, anyway, and so you have, so we could put all that in and calculate what the result here, okay, for the E. Okay, should we do that? Maybe we should do that once at least. But so this guy here is 72 gigapascal times BH cubed over 12. All of those are 2. All of those are 2. So it's at 16. So 16 over 12. So there's our EI over L, which is 10. And of course, we've messed up all our units and stuff here, so who knows what we've really got. So anyway, you get the idea. And so you can, all right, so what about this torsion spring here? We didn't talk a lot about this. I didn't show it, but it's gamma K theta EI over L. So gamma is 0.85. K theta you can approximate as 2.65. This here is twice as stiff as that guy. So we got 2 gamma K theta EI over L. And those are the same. So this is 4 times stiffer than one with just the force on the end. Okay, so then you would have all of your dimensions, all of your spring constants, and you can analyze that device. So just what we've done, we're just going to review for a second. And if you just internalize some of the things that we've learned today, you'd be able to design a lot of compliant mechanisms. Okay? So first of all, we talked about stiffness and strength not being the same, right? Talked about we can make things both flexible and strong. Talked about our 3 tools in our compliant mechanisms toolbox. And then we've shown 3 things that we can model using a pseudo-rigid body model: small length flexural pivots, fixed pin segments, and fixed guided. And we'll show probably one or two more. And that turns out to be, in the end, a lot of different things that you can design. If you start watching compliant mechanisms that you see that are commercially available and start to visualize their pseudo-rigid body model, suddenly you're going to find, like, oh, wow, I could have designed that. Okay? And you can and will, okay, be able to design that. All right. Let's going here. Something just seems odd. As a professor, I'm programmed to talk for 50 minutes, you know, because that's how long class periods are. So all of a sudden, my brain was saying, "Wait a minute, you're still talking? What's going on?" So yeah. The real problem is when you're supposed to talk for 15 minutes and you're programmed to talk for 50 minutes, you know. So, okay, let's look at another pseudo-rigid body model. Okay, and that is when something is pinned at two ends. Okay, so now, if I have something like this, let's say this is the flexible beam, and I have it pinned at both ends, then the only way that can react, the only way that can respond is by having forces that are aligned. So actually, here's another thing that's kind of non-intuitive. I'm showing a very simplified geometry there, but what if I had something instead that was fixed at this end, fixed at that end, but its geometry looked like this? I don't know what we want it to look like. Okay, so some crazy flexible geometry here. And then I'm going to load it just with forces at those two pin joints. It turns out, if I do that, let's say I put, okay, I've got a force here, but I don't know what direction it is. Let's call this Fy and this Fx. And this is Fy and this is Fx. If I do the free body diagram of this, let's say I sum the moments about this point right here. Fx is coming through that point, right? So it's not causing any moment. Fy, the moment about this point, is Fy times this distance. But there's nothing to react that moment caused by that vertical force. So the only way that can be in equilibrium, if this is only a force here, I'm not putting a moment, only forces here, the only way that can be reacted is if it goes to 0. That can't exist for it to be in equilibrium. And it turns out now I sum the forces in y, and all I have is this force. I want it to be in equilibrium, so what happens to that force? It can't exist. The only way this thing can be in equilibrium, I don't care what shape it is, the only way it can be in equilibrium, if it's pinned at both sides, is for those two forces to be aligned. Equal magnitude, opposite directions. Okay? So that acts just like a spring. So when you see this, then that just acts like a spring there, and I can model that then as a spring. And so we can come back to our, right, you see that because I just have forces here, and that's just going to compress or stretch. And this actually, as simple as it is, you'll find is in all kinds of interesting places. So in this case, we'll just show a circular thing like this. And the pseudo-rigid body model is then a spring. And What we don't have, though, with this is the spring constant does depend on what geometry we have, right? If I have some crazy thing like this, right, the spring constant's going to be different. And if you have, just over time, I've found that we run into this situation of a curved one quite often. And so because of that, then we also have, we have spring constants for that you can get out of the book and stuff. So, all right, and in this Handbook of Compliant Mechanisms, there is, in this book, there's an appendix that's specifically on, that shows kind of a library of pseudo-rigid body models and equations and stuff, plus all the derivations and stuff are in there. And then and the Handbook of Compliant Mechanisms also has a table, and I think Craig Luss may talk about that more tomorrow. So, okay. This is worth talking about here for just a minute. Now, what if we have a fixed? So now I allow both a force and a moment at the end here. And if we do that, then we don't get the nice, simple fixed free or the fixed guided condition. But you do notice that there's an inflection point somewhere. And if you look at that inflection point, you could possibly model that with two pseudo-rigid body models together as if they were connected there at that pin joint, or at the inflection point. They're not pinned, though. It's still rigidly connected. This turns out to be a fairly complex way to model this, though. So there's three ways you can model this for the pseudo-rigid body model. One is this, which, where that point's always moving, that's kind of hard to do. So it seemed like a good idea when we did it, but it turns out it's just, when you go to the pseudo-rigid body model, right, you're doing it because you want it simple, and if it's not simple, then why are you doing it? So another option is that we use quite a bit, actually, is to say, well, it's not fixed guided, but how about we use this model anyway and just deal with the errors that come up, with that, and it'll be good enough for preliminary design. So sometimes that actually will work. The third method is a method where you actually use three pseudo-rigid body models, or three pin joints and springs. And this method, it was developed by Haijun Su at Ohio State. And that's a good method for doing these kinds of beams. And others, Guiman Chen at Xidian University's added to that, and others have added to that as well. But if you look up those are helpful. Okay, and then there's others, putting on a pure moment load, initially curved beams, and there are others. And sometimes we've created pseudo-rigid body models that were just for specific problems that we were working on, and so that's another thing you can do. All right, so now it's your turn. Let's take a minute. I think this is going to use some of these in our library here. Get out your pen and a piece of paper. And let's see how you do in sketching the pseudo-rigid body model. First, put in all the pin joints of where they would be, or other things, whatever elements are there. And then the springs, and then start to write out as many lengths, just symbolically, because I haven't given you numbers here. And symbolically write the lengths and any torsional springs that you can do. Give you a couple minutes to do that. Okay, let's get started. Let's try this then. Okay, so here's our device. Let's start over here on the left and work our way right. Okay. So, what kind of a segment is this guy right here? Has a pin joint at one end, fixed at the other, but the fixed point is fixed to a rigid segment, but that rigid segment's moving all over. But so what is that? Let's come back here. Now we're at, we'll call this A, B, C, D. Yeah, it's B because it's fixed at one end. And we say fixed, it doesn't necessarily mean it's fixed to ground. It means that the relative, it's relative to the other end. And so that is, okay, so that's a fixed free there, where it's, fixed on one end, force on the other. And so how are we going to model that? Okay, we just saw that there, right? So it's going to be gamma L from the end. And so we've got that there. So we've got that point and that. Okay, so there's our pseudo-rigid link. And we'll put a torsion spring right there. And why on that end? Yeah, because that's closer. That's the closest to the fixed. So this is fixed. That one's pinned, right? So it's got to be up there. All right, so we're working our way over here. So that's that kind of element. We work our way over towards the right. And how are we going to model this short, flexible segment? Okay. Yeah, pin joint where? Right in the center. Okay, so we put a pin joint right in the center. And here's our torsion spring. Okay. Now, how about, and what's its, we should talk about the spring constants too. So this spring constant is K, is gamma, K theta, EI over L. What's this, what's that spring constant for a Smalling flexural pivot? Yeah, EI over L. So you find this EI over L is showing up everywhere. And we're going to come back and we're going to spend a minute talking about this after we go through this exercise here. Okay, so this guy right here, what's it going to be? Let's come back and look. Is it A, B, C, D? C. Okay, so C, because it's fixed guided here. So we can do this. And it turns out this one here is the same, right, on the other side. And notice, these lengths and stuff kind of change. I've got to go up and grab that point. And then I have 4 torsion springs. So here, K is equal to, it's related to this one. What's the difference between this torsion spring and that torsion spring? Yeah, this one's twice as stiff. So it's 2 gamma K theta EI over L. And it turns out all 4 of these have that same stiffness. So So this beam here is 4 times stiffer than this one if they're the same length, but the mechanism's 8 times stiffer than that. Okay. Now we just have one more left. Okay, what is this? This is pinned at both ends. So what's that going to be? Yeah, that's just going to be a spring that we can model there. And that spring constant, we could look at. And there's, it gets a little bit more complex because there's so many things that you can do with that, because it turns out the shape here doesn't really matter. And if you take some of you see this kind of thing, if you look on consumer products, on bistable lids, like on shampoo lids and stuff, and this shape will be whatever they need it to be to conform to the container. It's really pretty cool. Okay, so now what we have is look, you have a model now, a kinematic model that you could analyze using traditional kinematics. This crazy flexible blob, okay, it turns out you can analyze. And you could get the motion. You could have it do whatever performance that you want, have whatever force deflection you want, and so on. And this is... turns out to be very useful. Okay, so, yes? Okay? Oh, okay. All right. No, I misspoke there. It's not free. It is pinned right there, so it can't. It can rotate about that point, but it can't. But it stays right there at that point. When I said free, what I was referring to is if I just look at the beam itself, then I could find a point of view where this would be fixed at one end, and just where it just has a force on the other end. And sometimes we call that a fixed free condition. But when you put it in a system like that, that point cannot move. But there's also not a moment there. There's only a force reaction there because it's a hinge. There's no torsional spring there. And, yep. So the only reaction force I allow at that point is a force. Okay, so let's make another point here, and that is that this this is kind of crazy here, where we say that this model, I didn't say whether this was, so gamma is equal to 0.85, but what if that were titanium? Or what if I had two of them together? One was titanium. They're both the same length. Geometry is all the same. One's titanium and one's polypropylene plastic. What is going to be different in the location of their characteristic pivot of this pseudo-rigid hinge right here? One's polypropylene and one is titanium. What's the difference in the location? It's a trick question, by the way. There is no change. It is the same. Is that not weird? Is that not weird? But it's true. It's kind of cool. The fact that this works, no matter, it is not material dependent, that this gamma L, until you start yielding, right, and all that stuff, right? But still, so assuming you're not yielding the material and everything, that gamma, 0.85, that occurs in the same spot, whether it's steel, whether it's aluminum, titanium, polypropylene, wood, composite, I don't care. Okay, that stays in the same spot. What is different? What does change? But you say, but hey, I know that if I have to have a polypropylene and a titanium beam, and they're both there, and I deflect them both, They're not the same. So what is different? Yeah, this torsional spring, okay, is going to be different. And I say gamma. I say gamma doesn't change for the material. Here's what's freaky: is either does k theta. That constant there is also a unit. These are both unitless constants. Okay, and that's about 2.65. So these are both unitless constants. They're independent of material. So where is that coming in? If the geometry is all the same, where's the difference between polypropylene and titanium coming in? Yeah, in material properties, okay, in the Young's modulus. Okay, so that is another thing that's kind of interesting about the pseudo-rigid body model is the geometry. When we did this sketch for this pseudo-rigid body model right here, that motion is going to be the same no matter what material I put it in. Okay, I could have made this elephant out of a rubber instead of out of polypropylene, and it would have that motion. If I did steel, steel would yield, but that's another story. That's another problem. But really hard to do small length flexural pivots or living hinges and steels. It'll just yield. Sometimes that's okay. You just have it yield at all those small points and say, yeah, too bad. That's, small length yields and doesn't fracture. But anyway. All right. Any questions? Yes. Yeah, so I wish when I teach a class, I have this flexible beam that's steel about this long that I bring to class, but it doesn't travel well, So it's and we could. We could go through, let's see if I can do it quickly without doing the whole derivation here. But here I have this guy with this one spring, okay, and this one with these two springs, and then each individual spring is twice as stiff as this, and so we have 4 times the stiffness. And part of the difference, I think, that's a little bit confusing on this, is the fact that since it's fixed guided, if I just allowed this, if I only put a force right here, right, then it would behave differently. But I am forcing these to actually always be the same deflection. So they behave as if those two springs are in parallel instead of series. Yep, very good. You've worked with springs in series and parallel before. You're able to catch that nuance. Okay. See, there's something else I was going to say. It will come to me in a minute here. All right, any other questions? Yes? Yeah, so the gamma, how it was originally determined was just running an optimization routine to find what value of gamma best gave the best approximation for the longest motion. And so this is just, you can't derive it. It's just an optimized thing. Or maybe you could derive it, but you have to be smarter than me. And same thing with the k theta. Is if you looked at my first paper on this torsional spring was actually done as a 5th degree polynomial in capital theta, which is the angle you can model anything with a 5-degree polynomial, right? I mean, so, and then another grad student in the lab by the name of Tony Norton, he said, well, wait a minute, if this model really works, you should be able to do all this, you know, and he realized that this was just a linear spring. I mean, because the nonlinearities, it's very nonlinear, but the nonlinearities come from, you know, the motion of this, and then so he discovered that this was could be a constant even in this situation. And so it's still very nonlinear, but the nonlinearities come in. Maybe I should show that here. Sorry, Steve, man, I'm using all of your paper, dude. Yeah, we'll reuse here. So if I have a beam here, and I'm going to push on this and see where it goes, and here's my pseudo-rigid body model, and it comes up here to some point. Torsion spring here. Let's, you know, so we can figure out, let's say there's, you know, vertical force there. Right, we could figure out what the capital theta, what this vertical force is, let's call it, or vertical deflection, delta y. This has some delta x. But delta y, and this is gamma times L, right? So what is, if I know gamma L, I know that length, I know capital theta, can I calculate delta y? Yeah, it's just a triangle, right? Here's gamma L, here's capital theta, here's delta y. So delta y is just gamma L times sine capital theta. So that's pretty easy calculation. So it's kind of nice that gamma and k theta turn out to be linear, but the whole system as a whole isn't, because you end up with trigonometric terms. Now, if I put in, let's call this force right here, and I want to figure out what the moment that force is causing back here at the torsion spring. Okay, so let's just call that T for torque here. And what's the moment going to be caused by a force, that force at the end back here at the torsion spring? What's the moment arm going to be? Yeah, okay, so it said gamma L cosine theta. That distance right there is the moment arm. Gamma L cosine theta times the force. Oops, not E for that. So that's pretty easy, but it changes. This is what makes it nonlinear. As the deflection changes, the torque changes, even as with the constant, you know, same force there. So you have a nonlinear relationship, but it's still pretty darn straightforward for doing this. So it's pretty cool. Now I mentioned that I should also say that the displacement was within 0.5% of the motion. The force is not nearly as accurate. Okay, it's still quite accurate, but the force predictions, the k thetas have more of a more variation in them than that. So, okay. Any other questions? Good questions? Yes.
Yeah, if you wanted more accurate stiffness, of course, we could do an optimization for that.
Yes.
You lose on accuracy of.
Yeah. So, well, what we've done is is we usually do them independent, one for the motion and one for the spring. And usually the inaccuracy is coming just through through time. So we'll actually make the spring constant or whatever, say a function of theta or a function of the direction of the force. And then that will get a more accurate model. And I don't think I have any examples here, but sometimes when we're doing something that just has some weird loading condition, and we'll do that, we'll just create our pseudo-rigid body model and say, oh, for this problem, the gamma is really 8.37, and it, under these loading conditions. And so the 0.85 is really handy for just in general, but for specific problems, you can modify that a little bit too. And that's okay. Good comment. Yep, that's right. Yep. No, I mean, it depends. No, because you can, in the book, there's the equations actually that do that, and they're not so complex. Even something like a spreadsheet, you can still do it. It's not that bad. But usually when you're trying to visualize things and stuff, the simplified thing is better. But as soon as you code it, as soon as you put it in code, then adding some of those other things is not that hard. And a lot of those already exist. Some of them don't. And Dr. Craig Lusk back here has done some more pseudo-rigid body model things as well. There's a number of people that have contributed in this area on the pseudo-rigid body models, where you can see what they've done to get these different values and stuff for specific problems. So. Uh-huh. Yeah, and in those cases, sometimes they say we'll put in the more exact things and get there. Other times we'll use the rules of thumb and then go to FEA. Like on the safing and arming stuff, we may get to show the example, to show you the pseudo-rigid body model of that. And that helped us to make something that we would have never come up with otherwise. It's just too complex of a motion. The pseudo-rigid body model helped us to get there. But then we also refined it we went in with finite element analysis and did a lot of, and then that was a lot easier once we had at least the geometry that we were going to use, right, and got the complex motion and everything. So I don't know if that helps, but okay, anything else? Okay, great. And let's see, we've got a couple more minutes here, and then I'll show you. Remember this crazy-looking thing? Okay, I promised you we'd look at the pseudo-rigid body model here. So here's something we call a cross-axis flexural pivot. Okay, that has those two beams are not connected in the middle. Okay, they're allowed to deflect. So here I have it in another beam. So if we also ever interested, we've created a whole bunch of our own compliant Legos, okay? And so we have the files for those. If you want to create them, you can go to our website at BYU and just do compliantmechanisms.byu.edu, and you can create your own compliant Legos. So anyway, it makes prototyping really easy, right? Even super fast, even faster than usual, but. So this is a cross-axis flexural pivot, okay? And there's a model, pseudo-rigid body model for that. And it is basically putting the pin joint right in the middle, and a torsion, and then there's a torsion spring. It's a little bit more complex, right, because more stuff's going on. But as far as the motion goes, you can see that. So now you start looking at this, and you say, oh, wait a minute. That looks like just a cross-axis flexural pivot in titanium. Oh, wait a minute. So's that guy. Wait a minute. So's that guy. And wait a minute, so is this one. Oh, we're looking from another direction. And so is this one over here. So you say, oh, wait a minute, that's just a bunch of cross-axis flexural pivots. And there's also a split tube flexure in here, but that's harder to see. And so when you do that, all the mystery out of this thing goes away, because you find out that here's, well, you see, here's the output stage of what we're moving. Here's where we're connecting to the spacecraft. But now, where those, if I had put pin joints right where all those cross-axis flexural pivots are, then you see this becomes a lot like the rigid body model is a lot like the Agile Eye device that Clement Gosselin's group had done. And this is the compliant mechanism version of that. And so now you see again the compliant or the pseudo-rigid body model helping us get to something that looks complex, but really is not nearly as complex as what it originally seems. And so there's the pseudo-rigid body model of it as a 3D mechanism. And then here's another animation. I showed you an animation with the thruster. This is with it doing a communication satellite. It doesn't show anything new, but I spent a lot of money for these animations, so I got to use them when I can. So calculate, this is about $1,000 a second, it turns out, to get this quality of animation. So, and then I'll just mention origami. So you can also model these creases in origami as hinges. And so here we actually put it with hinges at the crease, real hinges, and then convert it back into a compliant mechanism with compliance. So we could go to something besides paper. And then here is another animation showing there's an origami vertex going to what turns out to be a spherical mechanism, because all of the joints come in and intersect at a single point. And so that, we don't have time to talk about the other stuff here, but I want to show you one other freaky thing with origami. So in the book, there's a little sentence that says, one of the disadvantages of compliant mechanisms is you can't have continuous revolution, right? And that makes sense. I can't hook a motor up to a compliant mechanism and have it continually rotate, right? I mean, that's just you don't need to prove that. It's just obvious. Well, no one bothered to tell the origami artists that, though. And so they created, it's called the kaleidocycle, which is a compliant mechanism with continuous revolution. Tell me that ain't freaky. And so here, we're like, okay, so that's paper, but I want to do something besides paper. So here we did it in polypropylene. And again, you can see continuous revolution of a compliant mechanism. And then going from polypropylene to acrylic, which is a brittle material, right? So this should just fracture. And by golly, there we have a continuous revolution of a brittle compliant mechanism. Because brittleness and strength are not, brittleness and stiffness are not the same either, are they? Ductility and stiffness. Brittleness is about how something fails. So you can make something brittle also flexible. Okay? So we do it in MEMS all the time with silicon. So anyway, so I just thought I'd end by blowing your mind with a... So if I ever write a new edition of the book, I've got to fix that, sentence. All right, thank you. I think we're ready for lunch, right? You're welcome to come up and look at some of things here. I'm going to I need to run just right after lunch, and then so feel free to take a glance now.
Larry, this is